like a huge priority, right?
Mm-hmm.
And I guess there's two ways of approaching safety. You can either have components that are super strong and resist deformation, or you can have like a crumple zone that absorbs the energy of an impact. And I'm guessing a crumple zone would be a lot more lightweight. So in this increasing focus towards the lightweighting of automobiles, have they made more components into crumple zones that absorb energy and have to be replaced after an accident instead of being tough enough to withstand it?
It depends what part of the car you're talking about. Okay, so that sometime long ago, I think General Motors did some studies with pigs, unfortunately, and they were trying to quantify what's the maximum G load that a human can survive. You know, so like if you hit something, you come to a sudden stop, right? There's some deceleration associated with that, and there's only so much of that deceleration, that G force, that a person can handle before they get permanently, injured. And General Motors, I think, determined that to be 29 Gs. Okay, so the way that the regulations are written is that a passenger can't be subject to higher than 29 G. So if that's the case, then there has to be crumple zones. You can't just make the front of the car, infinitely stiff and then expect in a front impact that the passenger or the driver wouldn't, or anyone in the car wouldn't sustain more than 29 Gs. You have to have crumple zones. But that's for front impact. So that's in contrast to like a side impact. A side impact, you're trying to keep another car outside of the inside of the passenger compartment. And in that case, they do use very strong martensitic steel bars in order to keep other cars from getting inside your car in a side impact. Also with roof crush, when a car rolls over, they try to provide enough strength so that the roof doesn't crush down on the passengers. So there's another case where they use a lot of martensitic steels or hot stamp martensitic steels in order to make sure that the roof doesn't crush down too far and damage, cause any injuries. So note that something to keep important in mind here is that with crush space, usually the packaging space is demanded by the engineering teams from the design group, the styling group, to make sure there's enough space in front of the car so you can get lots of crush. So if you look at the front of a Porsche, like the 996, like a 1996 or 1997 Porsche 911, they've got a lot of front overhang. So go pull up a picture when you got a chance. And the reason they have all that, it looks kind of ridiculous if you think about it, but they've got this huge front overhang in order to create enough crush space so that the passengers will never see more than 29 Gs. So there's plenty of packaging space. And a door, where you're trying to keep people out of the inside of the car, the thickness of your door can only be so thick until you've got no elbow space, right? And then you don't buy the car. So in that case, you're very much packaging limited, and you have to put a really, really strong material in there to stop from any intrusion in the passenger compartment. On a rear impact, there's usually plenty of crush space. So the most crush space is in a rear impact, actually.
You might want to hit your record button because anyway.
It is recording. I hit that already.
Okay, fine. Thanks. Sorry.
It is recording already. Yep.
Okay.
So I guess, does that answer the question? Does that make sense?
Yeah, that makes sense. Thank you.
Okay. Good question, though. Right. So I guess I'd like to start off by, apologizing for the last lecture. Some things went haywire in my house there, and there was some, we'll call it turbulence and interference, and I'm really sorry about that. Shouldn't happen again. And hope you can forgive it. Okay. So I'm going to share my screen now and start with lecture 2. Okay. Can everybody see this? Yes.
Yep. Yeah, I can see it.
Okay, good. Okay, so here's lecture 2. This is the start of lecture 2. And I'm going to start this lecture pretty much where I left off with the last lecture. Okay, so structural efficiency of a design is a function of both geometry and materials. You can't make a lightweight, structurally efficient vehicle unless you consider both the geometry of the components that are making the structure and the geometry of the structure altogether and the materials that go into it. Okay, that's where I'm probably going to start every lecture, right here. Okay, geometry and materials. Structural efficiency is a function of geometry and materials. Okay, so here's an example. I want to compare these two cars. On the left here is a Lotus Elise. It's a first generation Lotus Elise, and on the right is a Renault Sport Spider Sport. Both of these cars came out in the mid '90s, within a couple of months of one another. They have about the same footprint, meaning the width times the wheelbase, within about 8%. Let's say that the Renault is a little bit bigger. They both have small four-cylinder engines, about 1.8 or 2 liter little tiny four-cylinder engines. Both these cars were very innovative in that they were made from aluminum extrusions. Okay, so both Renault and Lotus got the idea actually from Honda, to glue together or bond or join somehow aluminum extrusions in order to make the primary structure of the vehicle, the structure that takes all the bending loads and the torsion loads and the impacts and everything. The bodywork on both these cars are made out of fiber reinforced or glass fiber reinforced plastic. Okay, but here's the big difference. Whereas the Renault weighed over 2,000 pounds, the Lotus weighed about 1,600 pounds. So 28% difference, huge difference, and that can't be accounted for by the difference in the footprint, the wheelbase times the average track. So what happened? What's the difference? The big difference is that the Lotus was bonded together using structural adhesive, it's an epoxy, whereas the Renault was actually welded together. So the individual extrusions for the Lotus were bonded together using a structural adhesive, and the individual extrusions were bonded together in the Renault using welding techniques. So again, on the left here is the body structure, the primary structure for the Lotus Elise, and on the right is the primary body structure for the Renault. Okay, so on the Lotus one, you see the aluminum extrusions, and then you see all this orange stuff at the goop, we'll call it, at the seams between the parts, at the joints. That orange goop is the structural adhesive. It's an epoxy. Okay, and then on the right here, you see you can see a little bit of the welding kind of in the middle. I don't know if you can see my cursor or not, but right here you can see a little bit of welding that's holding together, and up in here you can see some welding. It's holding together the aluminum extrusions in the Renault. So the difference is that because Lotus used an adhesive to bond together the extrusions, there was no heat affected zone. Whenever you weld something, you damage the material by heat. You change the intended microstructure to another microstructure, which may or may not be strong. Usually it's not as strong as the base material, and you end up with a weaker material. So Renault, in order to compensate for this reduction in strength, they had to use a much thicker wall extrusion. Whereas the Lotus, because they glued everything together, they used a non-thermal process. All the microstructure of the aluminum extrusions stayed the way they were from the get-go. They were able to use much thinner wall material, much thinner wall extrusions. And that's where the weight difference came from. It's the effect of this heat affected zone not being in the Lotus, but being in the Renault. I don't have a picture here, but on good quality steel racing bicycles, they use what's called butted tubing. Have any of you guys ever seen that? I don't know if you guys are into bicycles or not, but have any of you ever seen like that where you have like a, it says butted tubing, triple butted, double butted? Anyone seen that before? I can't quite see you guys. So the butting is what it is they use a thicker wall section at the place where the weld takes place in the steel. And then they thin it out as you go to the tube. So the tube has a varying wall thickness. At the ends where it gets welded, it's thick. And then for most of the center, it's very thin. Unfortunately, you can't really do that with an extrusion that I'm aware of. So although, theoretically, maybe Renault could have done that on the Spider, they didn't, because I don't think it really was possible. But that would solve the problem, but they didn't do that. So they have a much thicker wall than the Lotus, which is what led to the weight increase. So this is a circumstance where the weight of the vehicle really came down to the yield strength of the material divided by the density, so the so-called specific yield strength. So in order to make the most structurally efficient vehicles, okay, we're focusing on the material side in this lecture. In order to make the most efficient primary structures, the quantities to maximize from the materials perspective are the yield strength, the specific yield strength, and the specific stiffness. Okay, this isn't everything. These are sort of the primary drivers of weight of a primary structure, whether it's a bicycle frame or a car frame or airplane fuselage or, I don't know, a tank chassis, whatever. There are some other factors, obviously, fracture toughness, that's the ability of a material to contain a crack that's already existing in the material. Energy absorption, per the previous question, that's something that's very important. Obviously, in passenger cars, you want a material that can absorb a lot of weight, that doesn't absorb a lot of energy, that doesn't have a high density. Fracture toughness is another one. I'm sorry, fatigue resistance is another one. By the way, just to go back and circle back to that question, Lotus Elise actually has a very innovative fiberglass structure at the front of the vehicle that they use to absorb energy. As far as I know, I don't think there's any other passenger car that has a fiberglass crash structure at the front. Okay, so how do you create materials that have high specific strength and high specific stiffness? That's kind of the focus of the lecture today. So I'm going to start here. This is the fundamental paradigm of material science that we're looking here. These are the three interlocking loops of materials. The processing, structure, property, performance relationships in a material allow a smart materials engineer to design materials so that they perform better pretty much in anything. It could be an electronic property, but we're just going to focus right here on mechanical properties. So things like strength, and stiffness, fatigue resistance, fracture toughness. So I'll just a little history lesson here. So the field of material science, as it's called, material science, started in the early 1950s. The first material science department in the world was actually Northwestern University. This is the first time that any university pulled together like the polymer science and the metallurgy, ceramic science departments, pulled them together and called them material science. The early kind of, I don't know, age of material science really focused on understanding if you have a material like, you know, why is it strong? So I have this steel, the steel has been, I don't know, processed for eons, going back centuries. Some swordsmith was able to heat up this thing and hit it and bend it and heat it up and cool it and able to make this really strong steel. But why was it stronger than copper, or why was it stronger than a lot of other steels? And so the early part of material science really focused on understanding this strength, like why, you know, what is it that's happening in the microstructure of the material that's causing it to have these properties, these high strength, which gives it this performance. It's a sword that's good for cutting off people's heads. That was sort of where material science was focused for a couple decades. I think maybe in the kind of early to mid 90s, things begin to shift a little bit in material science. Materials engineers begin to ask, like, you know, how can we actually design materials so that they're strong? So starting, not taking a material and going backwards, you know, down, that's going from the right to the left on this chain, but actually going from the left to the right. So how can we start from the beginning and design materials that meet certain property objectives, strength or stiffness or fracture toughness or fatigue resistance? How do we go up this paradigm, these chains? How do we design materials? One framework for designing materials is called the Olsen Diagram, shown here. And this is a framework for understanding that, you know, when you make a material, you have to do different processing steps. You might have to cast it. You might go from a liquid to a solid in a casting mold. You may have to solution treat it, heat it up, let it homogenize, and then you might have to quench it, and then you might have to do some hardening or some aging to the material. These different processing steps lead to different microstructures, okay, and different microstructural features. So that there are really, in a lot of materials, what's called a hierarchy of different features in the microstructure. There's grains, there's precipitates, there's grains, precipitates, there's atoms that give cleavage resistance, there's atoms that change the grain size. There's a hierarchy of different sort of systems in the microstructure that lead to properties. The properties are things like specific stiffness or specific strength or fatigue resistance, or in electrical, it might be electrical resistance. And then these properties in a material, which came from the microstructure, which the microstructure was produced by some processing, lead to a performance that makes the material useful to people. So this might be a bicycle frame that's really stiff, and it's really lightweight, and it makes you go faster when you ride because you don't have to lug as much weight up hills. So this is, like I said, this is sort of the framework for how you go from the left to the right on that on those three links, on that fundamental paradigm of materials engineering. Okay, so we're going to kind of focus here on strength to density ratio, since in a lot of designs that becomes a limiting factor to produce the most efficient structural design. At the sort of center of strength of a metal are what's called dislocations. Okay, so metals, as you know, are made up of these regular crystalline arrays of atoms. When a material goes from a liquid to a solid, somehow magically through thermodynamics, the atoms line up in rows and columns, and they form crystals. This happens over and over again. Each grain is like a perfect crystal. Sometimes when these crystalline lattices, they're called, form, you get a missing column of atoms. That missing column of atoms leads to a distortion in the lattice, and that missing column is called a dislocation. If you're a physicist or a material scientist who's very, very fundamentally based or very fundamentally minded, and you try to calculate out what is the strength of a given metal based on the attraction between the atoms in the crystalline lattice, you will come up with a strength that is much, much higher than what you get out of real materials. And this is, remember I said back in the 50s when people focused on understanding why properties existed, they went down that those three links. They went from the right to the left. They discovered these dislocations, and that became the fundamental theory for why real metals were weaker than the theory of the attraction between the atoms would suggest. Okay, when you take a piece of steel or aluminum or titanium or nickel or beryllium, and you pull it, say, in tension, or you push into compression, those forces can be broken down into a stress based on the cross-sectional area. Okay, it can be resolved into a shear stress. When a material deforms in shear, you're moving that dislocation down the lattice, and that's what creates the shear deformation in a metal. Okay, so like I show in the diagram in the top here in 2D, as you shear this material, tau, you get this sort of movement, this sort of sliding of the dislocation, the missing column of atoms down the lattice, and that leads over millions, or whatever, thousands, millions, hundreds of thousands, tens of thousands, millions of grains, leads to a far field shear deformation that you can really see, right? And you guys can pull out a paper clip out of your backpack right now, and you could bend that paper clip, and exactly what you're doing as you bend that is you're moving those dislocations around. In 3D, material scientists often talk about a dislocation as a line. So if you think of a grain of material in 3D, a 3D lattice of atoms, and there's this missing column, then you can begin to think of the dislocation, where all those dislocations, all those columns line up. You can begin to think of this as a dislocation line. And actually, there are, believe it or not, if you can measure the length of this line, there's actually several kilometers of dislocation line, even inside a grain that's maybe 10 microns or 100 microns wide. So there's many dislocations inside a grain of material. You can reduce them or get rid of them by heating up the material and annealing them out, and then you can create them again when you start bending the steel or aluminum or titanium, whatever it is. When you start bending it back and forth, you can recreate these dislocations and move them around. But keep in mind that there are, like I said, kilometers, literally kilometers of dislocation line inside a grain that might only be 10 or 100 microns wide. Make sense, guys? Anyone? This is weird lecturing on Zoom, because it used to be when you lecture in front of people, they sort of shake their heads and you kind of know, but oh well.
I had
So
a question
the
about the dislocations.
Sure.
Can you explain just one more time where the source of the dislocation, why they occur in the material in the first place?
Sure. It's defects. They're defects. It's like it's just stochasticity. It just
Okay.
bad luck, if you want to call it that. Nothing in nature forms perfectly, and dislocations are part of that. There's obviously thermodynamics involved, as there is with everything, but they form kind of randomly by accident.
But do they only form around, like, if you have a different atom or a different material in that location, or can they form, I guess what I'm thinking of is like materials that you grow, like single crystals.
Right.
Would that limit these, or does it happen there as well?
So I think you're referring to things like single crystal nickel, like they use for turbine blades and jet engines to reduce creep. Or you might be talking about silicon, like wafers that are used to make computer chips. Those are monocrystalline. They have basically are one big crystal. They're not broken up into grains. So you have a continuous lattice that might go on for whatever, several centimeters or inches, that are all sort of the same orientation, or very close to the same orientation. But yes, you still end up with dislocations in that case too. Fewer, far fewer, and that's why single crystals can be brittle, like silicon wafers are very brittle. There are a lot less, but there still are dislocations in those materials. Answer the question? Okay, good. Keep asking questions, guys. Just feel free to interrupt me at any time, all right? That's what this is about. This is supposed to be a back and forth. Okay, so one way to improve the strength to density ratio of a metal is through what's called work hardening. I'm sure you guys have seen stress strain diagrams. You have a linear region where as you load up a component made of a metal, there's the amount of deformation that occurs is directly proportional to the amount of stress you put in. It's a linear relationship. As you keep increasing, eventually the material is going to hit what's called the yield strength. And then the stress strain curve keeps going up, meaning that as you apply more strain to the material, it's going to keep getting harder and harder to create more strain. The stress is going to go up, and the yield strength of the material continues to go up. Okay, and then even this is with plastic deformation. So you're out of the linear region at this point. If you unload at that point where you've created a little bit of plastic deformation, if you unload at that point and then load it back up, you'll find out that it takes more stress to get it to yield again. So the density of this material has stayed the same. Okay, you've put in this plastic strain. The density stayed the same, but the strength has gone up. So you really have increased the specific strength of the material, the specific yield strength of the material. The ultimate yield strength and the ultimate strength haven't changed, but the yield strength has gone up. So that's increased the strength of the material. The reason this happens is because these dislocations, if you can stop them from moving, if you can get them tangled up in something else in the microstructure, like a precipitate, a little oxide that's stuck in there, you can actually stop these dislocations from moving, which means that it takes them, or maybe not stop them from moving, but make it so that it requires more energy to keep them moving. That's what's creating this work hardening effect. Okay. The strength increase this hardening mechanism. You can see that it's related to the material and the grain size. Can you guys still hear me okay? Give me a thumbs up, Professor Egger, if you can still hear me.
I can still hear you.
Guys, can you still hear me okay?
You're breaking up a little bit, but not much.
So the yield strength, like I said, so with this cold working, that's this deformation, it's called cold working. the yield strength goes up, okay, but the elongation of the material, the amount you can deform it until it breaks, goes down, okay? Another mechanism to impede dislocation motion and therefore increase the strength to density ratio is called solid solution strengthening. There's two different types of solid solution strengthening. There's substitutional, where you take this lattice of atoms and you take a solute atom, okay, and you substitute one of the primary atoms of the material with one of these solute atoms. There's also another called interstitial, where rather than substituting one of the lattice atoms, you actually insert atoms between the atoms. You insert smaller atoms of the solute alloying element in between the atoms of the main material. So you can get substitutional when the radius of the substitutional solute atom is within about plus or minus 5% of that of the primary base material atoms. The typical increase in strength is about the shear modulus of the solute divided by 10. That's what you get from adding these substitutional alloys. An example of a substitutional alloy is brass. So the material is primarily made out of copper, and then you substitute some of the copper atoms with zinc. That's an example of a substitutional solution strengthened alloy. With interstitial solid solution strengthening, like I said, you insert smaller atoms that have a smaller diameter in between the main lattice points. So some small atoms that do this are copper, for example, carbon, which is a small atom, boron's a small atom, nitrogen's a pretty small atom relative to, say, iron. And the strength increase with this is actually much higher. You actually get 3 times the shear modulus per unit concentration increase of the solute. An obvious example of this one is steel. Steel is an alloy of iron and carbon. The carbon sits at the interstitial positions between the iron atoms. So that's an increase in strength associated with this interstitial method. So solid solution strengthening. This is again, these atoms that you put in there are usually very small. They're usually not more than a couple % that you're adding, and then so the increase in density can be whether that's a decrease or increase, can be very small, but the strength can go up dramatically, very dramatically. So this is an instance where you've improved the strength and stiffness of the material. The density, or strength to density ratio. The density has stayed the same, but the yield strength has gone up dramatically, okay? And therefore you've created a material, you've designed a material that's much stronger. That specific strength, the strength to density ratio has gone up. It's now a good candidate to make a more efficient structure from. So on the right here, there's a couple graphs that show that the amount of increase in yield strength, the amount of solute material that can be absorbed by the base material is a function of the electron structure of the solute atom. And also the one at the bottom here shows that, for example, with a steel, as you add more and more carbon, the strength goes up. You may decrease fracture toughness, that is the ability of the material to contain a crack within it without having that crack propagate, but the strength's gone up. And the more carbon you add, the stronger it gets, pretty much. There's a limit, obviously. There's a solubility limit. You can't just keep adding carbon forever. Another very potent method for improving strength to density is precipitation hardening. Okay, so when you add different materials to the base material, like an alloying element, if the thermodynamics are such and the size is such that they don't necessarily form solid solution, either substitutional or interstitial, you can form, what a lot of times it'll form are these things called precipitates, which are sometimes little oxide, little particles that maybe only a couple nanometers, a couple microns wide. And these little particles, these precipitation pieces, particles, they are very effective at stopping dislocations, or not stopping, but say making it more difficult for a dislocation to move through a lattice of material. The energy to move that dislocation through the lattice increases dramatically when you, in some cases, when you have precipitation strengthening. So one example of a material that's precipitation strengthened is 6061 aluminum, okay? So 6061 aluminum is really one of the big workhorses of the aluminum industry. There's lots of airplane parts, car parts, bicycle parts, wind turbine parts that are made out of 6061 aluminum. 6061 aluminum is primary alloy. Its primary alloy elements are magnesium and silicon. Okay, and materials will not form a solid solution with aluminum, and you get precipitation hardening in the 6061 aluminum. The way that this is done is that the alloy elements are mixed up. Okay, the alloy elements are mixed up, and then the material is heated up to what they call solution temperature, which puts all those alloy elements sort of, it makes it thermodynamically stable for them to sort of form a solid solution, to dissolve into the aluminum matrix. You quench this material, and then you start getting these little precipitates, sometimes only a couple nanometers wide, that begin to grow out of the aluminum matrix. And this will happen naturally. If you take a quenched, solution treated and quenched 6061 aluminum, you quench it on Monday, you put it on the side of the room, and then you wait till Friday. On Friday, you'll find that it's stronger. But in the real world, where you have to make aluminum quickly in order to make money, you don't have time to do that. So there's a step that's called artificial aging, where you will reheat the material to a lower temperature than you did for the solution treatment, and you will precipitate out these little precipitates in a much quicker fashion. So maybe only in a couple of hours rather than days. So there's a point, these dislocations, when they're small, they're most effective at stopping dislocation motion or making it require more energy to move a dislocation through the matrix. That's when they're small, the atomic planes and lattices of the precipitate line up with the material around this. We call this a coherent precipitate. Okay, when you have a coherent precipitate, in order for a dislocation to move through that precipitate, it has to cut that precipitate in half. That requires a lot of energy. Because of thermodynamics and the extra energy associated with having this interface between the precipitate and the base material, the aluminum, there is a driving force for these precipitates to grow, okay, with time grow. So if you continue to heat this material, say 300 degrees Celsius, if you continue to heat this material, these little precipitates will grow and grow and grow and grow. And at that point, they lose coherency with the material around them. That is, the atomic planes don't line up. And then when a dislocation comes its way, it's very easy for the dislocation just to move around the line of dislocation just to move around this precipitate. The material begins to lose strength at that point. So this precipitation hardening, as you can see, has improved the strength to density ratio because you haven't really changed the density much, only tiny, tiny fraction, but you can drastically improve the strength. Is there a question? Someone? Okay. So you improve the strength of the material, but you can also lose the strength as the precipitates get too big. Okay. I have been involved with situations where a supplier was tasked with making an aluminum part for my company, and then they decided to do they said they bought a build of 6061. They machined this part out. It worked fine. The dimensions were great. And then they decided for some reason to heat it up. They heat the material up and these precipitates grow. And then when they're done heating up, you have a material that has only 65% of the strength it's supposed to. And then you get a mechanical failure. I've actually was involved once with a company that was making an electric motor for something. And the housing of the electric motor was machined from an alloy aluminum. It wasn't actually 6061, it was a different aluminum. But it was a precipitation hardened aluminum. So this company machined out the housing for this electric motor. And then they had an operation called the hot drop, where they heated up this housing so it expanded. And then they forced into it the windings from the electric motor. This assembly of windings and laminates, steel laminates. And they would force it in there. And it turned out that they would heat these things up in a furnace that was next to the press station, and the way it worked out, the operators would leave this aluminum housing in this oven for like 24 hours, like it would stay in there for a long time. When we got the whole motor back, we started having failures. The aluminum housings began to crack. I took a hardness measurement using a Rockwell indenter and found that the strength was about 65% of what it was supposed to be. That's a big problem, right? That part's not going to survive in reality, in the real world. So I took a trip to Virginia, and out in the woodwork there, went to the plant where they were assembling these parts. And immediately I said, okay, what's that oven there? And what's the temperature? And how long do the parts stay in there? And sure enough, when we cross-sectioned the material and looked at the microstructure underneath the microscope, it was very apparent that we could see the precipitates were too big, okay? A good precipitate, usually you can't see with an optical microscope. Usually you need an electron microscope to see precipitates in an aluminum, for example. But we could see these things with a normal metallurgical scope at about 500x. So it was very clear what had happened. We actually went back and worked with the supplier to minimize the amount of time that it was in the oven and minimize the temperature of the aluminum, just to the point where you could just begin to insert the electrical windings and wires and so forth. So we solved the problem, but the supplier really should have known better that there's this over-aging or over-precipitation problem that comes with aluminum. Fortunately, they didn't. They knew more about electric motors, but they didn't know much about metallurgy. Okay. Another strengthening mechanism has to do with grain size. It's called Hallpet strengthening. And what this theory holds is that the yield strength of a material is inversely proportional to the grain size. So there's some controversy about exactly why material strengthens as the grains go down, but it has to do again with our friend the dislocation. Dislocations, in order to continue to have a material that deforms, need to be able to sort of hop over grain boundaries, the grains between these, the spaces between these atoms, in order to keep yielding. And if you have, the theory goes that if you have a real lot of small grains, you have a lot of grain boundary area, then it takes a lot more energy to get these dislocations to go over these grain boundaries. That, again, is an increase in yield strength. This mechanism, Hallpet strengthening, is a common way of strengthening steel. If you see a steel that has niobium additions, or columbium, they also call it, this is exactly what they're doing. So they're increasing the grain size in order to increase the strength. There's a company that makes a very old, storied, famous company that makes tubing for bicycle frames called Columbus, and they're in Italy. And they have really pushed the boundaries, I think, of steel technology for bicycle frames. And one of their most modern alloy development contains a lot of niobium. And this is exactly what they're doing. They're decreasing grain size by adding niobium. The niobium changes the energy associated with the grain boundary, so it becomes thermodynamically more favorable for the material to have a small grain size. Very, very, very potent effect. I don't know, how many of you guys are mechanical engineers and how many are materials engineers? I don't know how we can answer this, but for those of you in the material science department, one of the professors in your department, Professor Chris Hsu, has actually started two somewhat successful companies from this principle of strengthening through Hallpet. The first one is called Extalic, and the second one is called Veloxant. Extalic uses electroplating to deposit a nickel tungsten alloy on a substrate, like a copper or something. And of a Nicholson alloy on Spotify. Sorry?
Sorry. Alexa
okay.
was chiming in when you said nickel alloys.
Oh, okay. Alexa's listening, huh? That means Jeff Bezos is listening too. Okay, so the nickel tungsten alloy. So one of the issues with this type of strengthening is that if you heat a material up, because the grain boundaries have lots of energy associated with them, you get grain growth, and you can lose strength very quickly when the grains grow, because this Hallpet effect just goes away when the grains get bigger. On I have a friend that I was from grad school who was studying nanocrystalline nickel when he was a graduate student. And what they did is, this was in the lab of Julia Wertman at Northwestern, they would evaporate nickel and then refreeze it on a cold finger, like a piece of metal that's cool. And they would consolidate all these little tiny pieces of evaporated nickel and push them together to make a nanocrystalline nickel. So on Monday, it had 5 times the strength of a normal, or 5 times the strength compared to a normal nickel. And then they put it in a closet. By the time Friday rolled around, it was the same strength as a normal nickel, because what happened was, as the grains grew, just by room temperature thermodynamics, it lost its strength. Professor Shu, what he's been able to do is he's been able to so-called paint the grains of nickel with tungsten. And because of the thermodynamics associated with having that tungsten sort of paint on the grains, he's able to not only dramatically increase the strength of the material, but also able to make the material stable over long periods of time. So you don't get this grain growth because the thermodynamics are such that the grains pretty much want to stay the size they're at, even when they're deposited very small. So he gets some, incredible 3 or 4 times increase in strength over normal nickel from this technique. His second company is called Veloxant. They're out in Framingham, and they use a similar strategy in order to make the material thermodynamically stable and make sure the grain size stays constant and the strength stays high. But instead of using electrodeposition, they use powder metallurgy techniques. So they have powders that are made. These powders are already nanocrystalline, stable nanocrystalline on their own, and then they consolidate those powders through a sintering process. Because of the thermodynamics, the grains continue to stay small, and the material has an incredible increase in strength. Okay, the last type of strengthening mechanism the next strengthening mechanism we're going to talk about is transformation strengthening. This is very common, say, in steels. You get a steel, let's say, from the steel mill, and it's a nice and soft annealed steel. It's made out of ferrite. The ferrite is very soft, has lots of dislocations in it. This ferrite can then be solution treated at like 870 degrees Celsius. That turns it to austenite. Then you can quench this austenite, and if you quench it fast enough, there's not enough time for the austenite to turn back to ferrite, or completely back to ferrite. And what you can get is what's called a martensitic material. So very little ferrite, but you have martensitic material. The ferrite is body center cubic. The austenite is face center cubic. And then the martensite is body centered tetragonal. So these are the different phases of this material. The martensite, because it forms much smaller grains and has sort of more carbon locked up in it, it is much stronger than the ferrite. So this is a great example of transformation strengthening. Okay, this is a very potent method of increasing the strength to density ratio of a steel, and it's used very often on racing cars and bicycles and airplanes and tractors and submarines and any kind of structure you can think of that needs high strength steel is almost certainly always going to be a martensitic steel, or maybe it's a benditic steel, but usually martensite is very frequently used as a strong phase to use in a steel.
Sorry, can I ask a question?
Please.
How is that way of making martensitic different from perlite or pearlitic steels? Because it seems like, because pearlitic steels also have ferrite and cementite.
Right.
Is it just the ratios of the cementite to the ferrite that distinguishes the difference between the pearlitic and martensitic?
Yes, but I can't remember if perlite is BCC or FCC. I can't remember, but it's the same thing. It's another way of transformation strengthening. You can create a pearlitic microstructure and still end up with something stronger than the ferrite you started with. So it's different in that the temperature cooling regime or schedule is different. You sort of cool at a different rate, and maybe you have some isothermal holds on the way down from solution treating, but it's the same strategy pretty much. It may not be as effective as martensite, but it's pretty much the same strategy.
Okay, thank you.
So the final strengthening mechanism I'm going to talk about here is using a composite. So I'm sure a lot of you guys have seen carbon fiber composites. Like me, it may be what really piqued your interest in material science to begin with. Carbon fiber uses two different materials in order to increase the strength. The carbon fibers themselves are incredibly strong and incredibly stiff, but on their own, they're kind of like wet noodles. You're not going to do much with it in any kind of bending or whatever if they're not consolidated, held together by a matrix. The matrix, in most cases, really high strength carbon fiber is epoxy. The epoxy serves to transfer the load from one fiber to the next. And through making this composite of carbon fiber and epoxy, you're able to get a very, very strong material. One thing I haven't talked much about so far is improving the stiffness to density ratio, because a lot of structures are not strength limited, but rather stiffness limited. So increasing or creating a composite is one of the few ways you can engineer a material to be stiffer than it would be from the base material. Most steels, stainless steels, high alloy steels, low alloy steels, carbon steels, pearlitic steels, all have very close to the same Young's modulus. Changes very little. There is some changing it, but it's only a couple of percentage. So you can't really get an increase in stiffness by the strategies I showed you before, by alloying either aluminum or steel. You can't really increase the stiffness to density ratio. But by forming a composite, you can very readily improve the stiffness. And there aren't just, I don't know how much you guys know about composites, but there aren't just sort of these, carbon fiber with epoxy matrix, carbon fiber, fiberglass, polymer matrix. There also are what's called metal matrix composites, where you can put say a ceramic fiber in aluminum. So the 3M Corporation makes some very, very strong aluminum composites by taking aluminum oxide fiber called Nextel and then infiltrating it with molten aluminum and then cooling the aluminum. And that forms a composite of aluminum and aluminum oxide fibers. Very, very, very strong, very, very stiff. I have actually a panel in my backpack here that is made out of this material, which I'd love to show you guys because it's incredibly stiff compared to normal aluminum. If we were in class, I would pass it around the room, but unfortunately I can't do that. So, okay, so this is another mechanism of increasing both strength and stiffness of a material, is to form a composite. And the strength increases and the stiffness increases will go with the law of mixtures, as you can see from these equations here. Okay, I want to talk real quick about design and materials now that we've gone over these different strengthening mechanisms, and give you an example from the steel world. So this is an Olsen diagram for a martensitic steel. On the left here are the different steps processing steps that you use to make steel. I've mentioned some of these already. You start off with iron ore, that gets refined, the impurities come out, deoxidize. Okay, you have to take the oxides out of it to keep the material strong, to keep the steel clean, to keep the grains attached to one another. Work hardening, increase the dislocation density. Solution treating, like we mentioned, austenitize at 870 degrees Celsius, and then quench, and then temper. The tempering is the precipitation hardening. So steel, like aluminum, doesn't always, but can strengthen through precipitation hardening. These are the different processes that you use in order to make a steel. But these processes dictate or translate directly into different features in the microstructure. A lath martensite is one of the highest strength materials there is. Adding nickel in the refining stage will increase the cleavage resistance of the material, so the sort of grain-to-grain strength. The strengthening dispersion, so that's the precipitation hardening, that requires tempering. So you can see there's a link between tempering and the strengthening dispersion. Grain refining. Remember I talked about Columbus tubes on bicycles and niobium. So niobium is often added as an alloying element to steel to decrease the grain size and increase the strength. You can increase the toughness, the fracture toughness of a steel by adjusting the chemistry such that when you quench it, not all the austenite goes away. Some of it stays there. And then because the austenite is only metastable, when a crack hits it, the energy from that crack can cause it to transform to martensite. And then there's a volume expansion associated with that transformation from the austenite to the martensite. And that can effectively clamp or reduce the stress concentration of a crack tip, which results in toughness. So that's the property section. And on and on. There's papers and papers and papers you could read on this topic, books you can read on this topic about designing steels. Okay, you have these different processing steps: tempering, solution treating, deoxidizing. The way you engineer these steps, these processing steps, dictates, translates to a different microstructure. Okay, so you as an engineer can pick the parameters for these different processing steps, and that can turn into the microstructure that you wanted, the microstructure that you know leads to a certain property, a strength, a toughness, a stiffness. You know these things. You know that microstructure becomes these properties. You get a material that has high strength, high stiffness, high fracture toughness, high resistance to hydrogen embrittlement. And this results in a part that has high performance, a part that will carry you across the finish line if you're racing a car, or get you up a hill if you're racing bicycles, or get you deep down in the ocean if you're in a submarine. This is very powerful. It's a very powerful concept of designing materials. And the US government has largely bought into this too. If you remember when President Obama was president, he initiated the Materials Genome Project. And this is part of what's called the ICME program. So Integrated Computed Materials Engineering. The US government has funded a lot of research in using computers, modeling techniques, simulations, that all come out of these paradigms here, these processing structure for properties relationships, to model all these different steps so that you can design a material on a computer without actually having to heat anything up or blend any ores together or any atoms or anything, just all virtual. And there are computer programs and simulations that get you from the first link, the processing to the structure. So if I temper at this, what size precipitate I get? If I temper at this other temperature, what size precipitate am I going to get? If I put in this niobium, what's the grain size going to be? There's computer programs, simulations, codes that have been written to predict this link between processing and structure. And then there's other codes available that get you from structure to properties. So if you know the grain size is this and the material is made out of that, what's the strength? If you know there's this much retained austenite in the material, what's the toughness going to be? And this is all recent. This all happened within the past maybe 10 or 15 years or 20 years that materials engineers have been able to do this, to create simulations that fill in the information between these three links between properties or processing and structure and properties. Very important stuff, guys. This is the future. This is what's really growing in materials engineering right now. Okay, final note, and I know I'm late here by a couple minutes. I just want to give you a historical perspective. I just want to introduce Professor Greg Olsen. As you see in my lecture, so I'm going to mention a couple people who've contributed, I think, very importantly to the field of material science and structural optimization. So Professor Olsen received his undergraduate and graduate degree at MIT under Professor Morris Cohen. He was a research associate at MIT for many years, and then he transferred to Northwestern University to focus more on metallurgy and design of materials. He was at Northwestern from 1988 to 2019, and interestingly, he just came back to MIT. So he is now one of your professors. He's up there on the 4th floor on whatever building that is behind the Infinite Corridor. You can go talk to him if you're interested to learn more about it. He started a very successful company called Questech Innovations in 1997. And this material specializes in using these ICME techniques to design materials from first principles. So I consider him a pioneer and a leader in the design of materials. He may be the father or one of the fathers of integrated computational materials engineering, ICME. He's the founder of the Steel Research Group at Northwestern, founder of Questech. He's a member of elected a member of the National Academy of Engineering. And most importantly, maybe to me, is that he has a world-class taste in cars. And this is his Lotus Elise right here. You see it right there with him jumping out of it or jumping into it. It's red Lotus Elise here. And again, this is the car that I showed you on the first slide. This is a later version of the car, but the same idea. This is the aluminum structure with the bonded pieces. But He also has a Lotus Elan, which was built in the 60s, made out of a lot of fiberglass. Neat car. So that's the end of today's lecture. Until next week. I'd be happy to answer any questions. I can stick around pretty much as long as you need me to.
Hi, Dr. Baskin. I had a question about the Veloxink material. Do you know what they use to sinter those nanocrystalline powders without grain growth?
The actual atmosphere is proprietary. I can't tell you that. And the temperatures and the pressures are proprietary. I can't tell you that. But I can tell you that they can sinter because they have effectively painted the grains with some solute that stabilizes the grain size.
Okay. And does that grain, are they still stable even at elevated temperatures? Because that sounds like an issue. Like if you'd
Right.
want to operate these chromium tungsten composites or crystalline nanocomposites at temperatures above like 600 Celsius, right? Or otherwise you could just use normal iron PM parts. So
Or nickel-based superalloy powder part.
yeah.
Yeah. So they are stable. I can't remember the exact temperature, but it was shockingly high. I can't remember what it was. Eventually you're going to get grain growth. When you get into 1,000 degrees Celsius, eventually you're going to get grain growth. It's just a matter of thermodynamic certainty. But they're more stable than any other nanocrystal material I've heard of personally.
Okay. Is there anywhere I could learn more about it without running into confidentiality or signing something to not disclose anything? Because it just seems like an interesting technology.
Yeah. Professor Shu has published a number of papers on the topic. I can let me grab a pen here. Let me see if I can send you some. It's not going to happen in the next 10 minutes, but let me see if I can send you some citations. I do have some papers in my library from Chris on Veloxink material. But you can also just go knock on his door. He's a nice guy. He loves to talk. He's going to love me for saying that because he's going to have all these students at his doors when he's trying to get stuff done. Okay, Miles. So I will send you some citations for some of his papers. What's your email?
I can send it to you in the chat. There we go.
Okay, great. I'm not looking at that screen right now. I'm looking at the.
Oh, okay. It's it's my first name and then another S.
Okay.
At mit.edu.
So no periods between Miles and S?
Nope.
Okay.
All one
Let's
word.
see if I can get some stuff to send you, okay?
Cool. Thank you so much, Dr. Baskin. I appreciate
You're
it.
welcome. You're welcome. Any other questions? Going once, twice, 3 times? Okay. We'll look forward to talking to you guys next week on Thursday, okay?
Hey, Professor.
Have a good one. Bye.
Thank you.
All right.